तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. This is the fourth lecture of Module 5 on Analysis and Design for Shear and Torsion. In this lecture, first we shall study the stresses in an uncracked beam due to torsion. Then we shall study the crack pattern under pure torsion. We shall study the components of resistance for pure torsion. We shall learn about the modes of failure, and finally about the effect of pre-stressing force. The analysis of reinforced concrete and pre-stressed concrete members for torsion is more difficult compared to the analysis for axial load or flexure. The analysis for axial load and flexure are based on the following principles of mechanics: equilibrium of internal and external forces, compatibility of strains in concrete and steel, and third, the constitutive relationships of materials. The conventional analysis of reinforced concrete and pre-stressed concrete members for torsion is based on equilibrium of forces by simple equations. The compatibility of strains in concrete and steel reinforcement is not considered. The strength of each material, concrete or steel, corresponds to the ultimate strength. The constitutive relationship of each material relating stress and strain is not used. When we studied the analysis for axial load and flexure, we had used the three principles of mechanics distinctively: the equilibrium of forces, the compatibility of strains, and the constitutive relationships. In the conventional analysis for torsion, we use only the equilibrium of forces. We do not use the compatibility of strains between concrete and steel, neither do we use the constitutive relationship of each of the materials which relate the stress or strain. Regarding the material behavior, we just use the ultimate strength of each of the materials at the failure. This way, we are doing a simplified analysis for torsion. There is more developed methods for analysis for torsion, which we are not discussing in this lecture. Torsion in a member can be classified into two types based on the necessity of analysis and design for torsion. First, the equilibrium torsion. This is generated due to loading eccentric to the centroidal axis. For example, in a beam supporting cantilever slab or precast slab or floor joists on one side, in a bridge deck subjected to eccentric live load, the torsion is higher for a curved bridge deck. And third, in an electric pole subjected to loads from wires on one side. The torsion demand is determined by equilibrium condition only. The member needs to be analyzed and designed for torsion. Here we are seeing two examples where torsion is common. A bridge deck is subjected to torsion when the wheel loads from the vehicle are eccentric compared to the centroidal axis passing through the CGC. For an L-beam, if it supports floor joists or precast slabs on one side, then the load is also eccentric to the centroidal axis. These sections are subjected to equilibrium torsion. In equilibrium torsion, the analysis can be done based on equilibrium of the forces only, and the members have to be designed for torsion because there is no chance of redistribution. Usually these members are statically determinate members, and hence we have to design for torsion because there is no redundancy in the members to resist torsion. The second type is the compatibility torsion. This is generated by twisting to maintain compatibility in deformation with the connected member. This type of torsion generates in a primary beam supporting secondary beams in a grid beam system. In compatibility torsion, the torsion demand is determined by both equilibrium and compatibility conditions. The primary beam need not be analyzed and designed for torsion if the secondary beams are designed as simply supported. The compatibility torsion generates in statically indeterminate system. For example, in a grid beam system, the secondary beams apply torsion to the primary beams supporting the secondary beams, and this torsion can be determined if we analyze not only the equilibrium condition, but also the compatibility of deformations of the secondary beam and the primary beam. The primary beam need not be designed for torsion if we design the secondary beams as simply supported. That means we are not considering any moment connectivity between the primary beam and the secondary beam. The code allows us to neglect torsion if it is a case of compatibility torsion. Here, the emphasis is laid on equilibrium torsion. To understand the behavior of a beam under torsion, the presentation will be in the following sequence. First, stresses in an uncracked, which is considered to be homogeneous, rectangular beam without prestressing due to pure torsion, that means in absence of flexure, with constant torque along the span. Usually, the civil engineering structures subjected to torsion are non-circular in section. Hence, we shall study rectangular sections. And first, to understand the behavior under torsion, we shall be addressing only pure torsion, where we are not considering any bending effect in the beam. And we shall also consider a constant torque along the span of the beam. Next, we shall study the crack pattern under pure torsion. We shall study the components of resistance for pure torsion. The modes of failure under combined torsion and flexure will be addressed next. And finally, we shall look into the effect of prestressing force. Although pure torsion is absent in structures, understanding the behavior of a beam under pure torsion helps to analyze a beam under combined torsion, flexure and shear. As I had mentioned before, that the behavior under torsion is more difficult to understand compared to the behavior under flexure. We are studying the behavior only for pure torsion. That means the beam is not subjected to simultaneous bending or shear due to bending. Now, this is not common in civil engineering structures, but still the understanding of a behavior under pure torsion helps us to analyze a beam under combined torsion, flexure and shear due to flexure. First, we are studying the stresses in an uncracked beam which is subjected to pure torsion. Here, the beam with the rectangular cross section is subjected to a torque tau. The torque is constant throughout its length. If we look into the cross section of a beam at a location, we will observe that shear stresses are generated in the cross section of the beam. These shear stresses will be termed as torsional shear stress, and it is different from the flexural shear stress that we had seen earlier. The torsional shear stress will be denoted as tau, and its variation is shown in the diagram on the right. It is 0 at the center, which is the center of the rotation, and as we move out, the shear stress increases. It is maximum at the mid depth of the longer side. It is also high at the mid depth of the shorter side. The relative values of these two values and the two sides depend on the ratio of the two sides. If we go along a diagonal, we will observe that there is no shear stress at the corner. Thus, the maximum shear stress that occurs in the cross section is at the mid depth of the longer side. We shall study the principal stresses and the Mohr circle for a member which is at the mid depth of the longer side, and here it is denoted as 1. At any point in the beam, the state of two-dimensional stresses can be expressed in terms of the principal stresses. The Mohr circle of stress is helpful to understand the state of stress. Before cracking, the stress carried by steel is negligible. When the principal tensile stress exceeds the cracking stress, the concrete cracks and there is redistribution of stresses between concrete and steel. It is easy to understand the behavior first for an uncracked beam which is considered to be homogeneous. The presence of steel in an RC member can be neglected before the cracking of concrete because the stress carried by the steel bars is very small. Thus, before cracking, we are studying the RC beam as an homogeneous beam, and if we pick up an element which is at mid depth of the longer side, then we are able to understand how the principal stresses are oriented for that member, and then how the cracks will form when the maximum principal tensile stress crosses the tensile strength of concrete. For a point at mid depth of the longer side, which is denoted as element 1, the torsional shear stress is maximum. This element is under a pure torsional stress. We are not considering any stress due to warping. The principal tensile stress sigma 1 is inclined at 45 degree to the beam axis. For this state of pure torsion, the principal tensile stress sigma 1 is inclined at an angle alpha which is equal to 45 degree, and the principal tensile stress is denoted as sigma 1, and the principal compressive stress is denoted as sigma 2. For a pure torsion, the sigma 1 and sigma 2 are equal, and when we draw the Mohr circle, it is symmetric about the vertical axis, and we see that a vertical face will be represented by a point in the vertical axis. Sigma 1 and sigma 2 are located at equidistant from the origin. Since the torsion is maximum at mid-depth of the longer side, cracks due to torsion occur around the mid-depth and perpendicular to sigma 1. With increasing torque, when sigma 1 exceeds the tensile strength of concrete, we observe a crack in the concrete which is perpendicular to the direction of sigma 1. That is, the crack is inclined at 45 degrees to the axis of the beam. Next, we are studying the crack pattern under pure torsion. The cracks generated due to pure torsion follow the principal stress trajectories. The first cracks are observed at mid-depth of the longer side. Next, cracks are observed at mid-depth of the shorter side. After the cracks connect, they circulate along the periphery of the beam. Let's try to understand by the help of the diagram. What we see here is that the first cracks occur at the mid-depth of the longer side. They are inclined at 45 degrees to the axis of the beam, and this is the first stage of initiation of torsional cracks in the longer side. Next, with increasing torque, we observe that more cracks have formed in the longer side as well as cracks have formed in the shorter side, and even the shorter side the cracks are inclined at an angle of 45 degrees to the axis of the beam. Finally, when the crack has formed substantially, they merge together and form a spiral crack along the length of the beam. These cracks are circulatory in nature, and this is typical for beams under pure torsion. Let's observe the crack formation once again. What we are observing here, that at the beginning there is some cracks at the mid-depth of the longer side, and next with increasing torque we find more cracks in the longer side and some cracks in the shorter side, and with further increase in the torque we find that the cracks have merged and they have formed a spiral pattern along the periphery of the beam. In structures, a beam is not subjected to pure torsion. Along with torsion, it is also subjected to flexure and shear. Hence, the stress condition and the crack patterns are more complicated than shown before. Earlier, we had seen the behavior of a beam under bending and shear due to bending, and here we have seen a beam under pure torsion. Usually, a structure is subjected to combined bending, shear and torsion. In such a situation, the crack formation is more complicated and it depends upon the relative magnitude of the flexural moment and the torsional moment. Next, we are moving on to understand the components of resistance for pure torsion. After cracking, the concrete forms struts carrying compression. The reinforcing bars act as ties carrying tension. This forms a space truss. Since the shear stress is larger near the sides, the compression in concrete is predominant in the peripheral zone. This is called the thin-walled tube behavior. Here, we are introducing two concepts. The first is the truss behavior for concrete under torsion after the cracking. For shear, we had seen that after the concrete cracks, the concrete and the steel forms a planar truss where the concrete forms the compression struts and the compression cord at the top, whereas the steel bars form the ties. The longitudinal bars form the tensile cord at the bottom. The stirrups form the vertical ties connecting the struts with the tensile cord. For torsion also, there is a truss behavior after the cracking of concrete. Here, the concrete forms struts which are circulatory in nature, and the steel bars, both the longitudinal and the transverse bars, tie these struts together, and this forms the truss action, which is called the space truss analogy for a beam under pure torsion. There is another concept which is called the thin wall behavior. Since the shear stress is more towards the periphery in a section, the resistance of concrete comes more at the periphery than at the interior region. Thus, the truss action actually is in the periphery of the beam. The interior of the beam does not carry substantial stress to resist the torsion. If we look into the truss mechanism, we can neglect the material of concrete which is inside, and we can just consider the shell outside the interior region, and this part of the member actually resists the torsion. The concrete has formed struts which carry compression. The steel reinforcement, which are both longitudinal and transverse, they form ties. Here the longitudinal bars are shown with axial tension which is generated due to torsion. Thus, torsion generates stress in the longitudinal bars as well as the transverse bars. Here the stresses are shown for a vertical section, and if we consider a horizontal section, then we can observe that the transverse bars are also under tension, and the concrete struts, the longitudinal bars and the transverse bars, they together form the space truss which resists the torsion after the cracking of concrete. The components can be denoted as below. We have the first component Tc, which is the torsion resisted by concrete, and next we have Ts, which is the torsion resisted by the longitudinal and transverse reinforcing bars. The magnitude and the relative value of each component change with increasing torque. That means, when a beam is resisting the torsion, both the concrete and steel are taking part in resisting the torsion. The concrete takes the component which is denoted as Tc. The steel reinforcing bars take the component which is denoted as Ts. And in the space truss, both the concrete struts and the steel ties perform together to resist the torsion. Next, let us study the modes of failure. For a homogeneous beam made of a brittle material subjected to pure torsion, the observed plane of failure is not perpendicular to the beam axis, but inclined at an angle. This can be explained by the theory of elasticity. If we take a piece of chalk and try to apply a torque in the chalk, then we can observe the failure plane in the chalk piece. This failure plane is not a planar surface, and it is not vertical to the axis either. It is a curved surface which is inclined to the axis of the beam. Let us see this in this photograph. Here, a piece of chalk, which is a brittle material, has been subjected to a pure torque, and we can observe that the failure surface is curved and it is inclined to the axis of the beam. If we take a rectangular piece of chalk, then also we shall observe the same behavior, but in a rectangular section, the plane of failure is further influenced by warping. Torsional warping is defined as the differential axial displacement of the points in a section perpendicular to the axis due to torque. That means when a pure torque is applied, the points in a particular section do not remain as a vertical section. The points have an axial displacement, and that is called warping in the section. Now, this is the behavior we have observed for a homogeneous material which is brittle in nature. In reinforced concrete, the concrete is tied with the steel bars, and once the concrete cracks, it tries to expand, but the steel ties hold them together. But as the torque is increased, the steel ties and the longitudinal bars will yield, and the expansion will be again seen. Thus, for a reinforced concrete beam, the length increases after cracking and after yielding of the bars. This is the mode of failure for a reinforced concrete beam under a pure torsion, that once the material has cracked, then the steel will yield, and finally the concrete will crush along the diagonal compressive struts. If the steel does not yield, then the concrete will crush, and that will be a brittle failure. But if the steel yields, then we shall have some ductility in the behavior of the beam under the pure torsion. For a reinforced concrete beam under combined flexure and torsion, the modes of failure is explained by the skew bending theory. The observed plane of failure is not perpendicular to the beam axis, but inclined at an angle. The curved plane of failure is idealized as a planar surface inclined to the axis of the beam. We have understood the complicacy of the analysis for a beam under pure torsion. If we are analyzing a beam under combined torsion and flexure, then the analysis is even more difficult. The analysis is based on the skew bending theory, where we try to identify the surface of failure as a planar surface which is inclined to the axis of the beam. Skew bending means the bending is occurring not along the transverse axis of the beam, but the axis of bending is occurring which is skewed to the longitudinal axis of the beam. Let us understand this by the help of a diagram. The skew bending theory explains that the flexural moment, which is represented as mu, and torsional moment, which is represented as Tu, combine to generate a resultant moment inclined to the axis of the beam. This moment causes compression and tension in a planar surface inclined to the axis of the beam. For a beam under flexure, we have mu. A plane section remains plane as per the Bernoulli's hypothesis for a beam under flexure. For a beam under pure torsion, we have just Tu, and what we have seen that for a beam under pure torsion, the plane surface is not plane anymore. The failure surface is curved and it is inclined to the axis of the beam. Under combined moment and torsion, we identify a resultant moment which causes the failure of the beam, and the failure surface is inclined to the axis of the beam. The curved failure surface is idealized as a planar surface for the purpose of analysis, and in the planar surface one part is in compression and the other part which is in tension. There the action of the reinforcing bars come into play. Thus, the skew bending theory analyzes a beam under combined torsion and flexure by considering a resultant moment which causes failure in a surface which is inclined to the axis of the beam, and part of that surface is in compression and the tension is taken by the steel ties. The modes of failure are explained based on the relative magnitudes of the flexural moment and torsional moment at ultimate. What we can appreciate is that two moments are acting in the beam, the flexural moment and the torsional moment. The failure depends upon the relative magnitude of these two moments, and the modes of failure are identified based on these relative magnitudes. Three discrete modes of failure are defined from a broad spectrum. The plane of failure and the resultant compression and tension are shown for each mode of failure. As per the skew bending theory, three modes of failure are identified for a reinforced concrete beam under combined flexure and torsion. In the first mode of failure, which is called the modified bending failure and is denoted as mode 1, this occurs when the effect of mu is larger than that of tu. Thus, the beam is primarily under flexure, but there has been some amount of torsion which has skewed the plane of failure. The plane of failure is not perpendicular to the axis anymore, and what we find that in this plane there is a zone which is under compression, which is shaded by blue, and the tension is carried by the bottom steel. Here the beam is under predominant flexural moment, the bottom steel is taking the tension, the top of the beam is under compression, but the failure surface is not perpendicular to the axis anymore, it is skewed, and that is the effect of torsion which has modified the plane of failure from that of flexure. The second mode of failure is called the lateral bending failure, which is denoted as mode 2. This is observed in beams with thin webs when the effect of mu and tu are comparable. Here the zone under compression is along the lateral side, and we can observe that the longitudinal reinforcement in the opposite side to the compression are in tension. This type of failure is observed when the web of the beam is thin and the magnitude of torsion is now comparable to the magnitude of the moment, and hence the effect of torsion is substantially high, and it has changed the mode of failure from a compression at the top to a compression at the lateral face. This mode of failure is thus called the lateral bending failure, where the crushing is at the side of the beam and the yielding of the bars occur at the other side of the beam. The third mode of failure, which is the negative bending failure and denoted as mode 3, when the effect of torsion Tu is large and the top steel is less, this mode of failure occurs. In this case, the magnitude of torsion is substantially high than that of the flexure, and if the top steel is less then the top steel will yield and the crushing will occur at the bottom. Remember that under pure torsion, the crushing can occur at any side of the beam depending on how much reinforcement has been provided. The modes of failure that has been identified here are 3 discrete modes of failure from a broad spectrum, and the design is based on 3 modes of failure. The first one is the modified bending failure, where the beam is predominantly failing under flexure with some effect of torsion. There the concrete is under compression at the top and the steel bars at the bottom are in tension, which is similar to what we have seen under flexure. The second mode of failure is the lateral bending failure. Due to the effect of the torsion, the crushing is occurring at the side of the beam and the steel bars on the other side are yielding and carrying the tension. When the torsion is substantial and there is less steel at the top, then we may observe that the crushing is occurring at the bottom and the steel at the top is yielding. Thus, the design of torsion will also follow to check these 3 modes of failure. Next, let us understand the effect of prestressing force. In presence of prestressing force, the cracking occurs at higher load. This is evident from the typical torque versus twist curves for section under pure torsion. With further increase in load, the crack pattern remains similar, but the inclinations of the cracks change with the amount of prestressing. If we study the behavior of beams under pure torsion, we will be able to plot the torque versus the twist curve for this beam. And if we compare the torque versus twist curves for a rectangular section with that of a prestressed section, then we will be able to understand the effect of prestressing in the behavior of the 2 beams. Now, in this figure, we are comparing 2 beams with equal ultimate strength. For the reinforced concrete beam, the beam cracks at a certain level, and then after cracking, the twist increases, and after that we see the nonlinear behavior due to the nonlinear behavior of concrete. Either of the steel, the longitudinal or the transverse, can yield first depending upon their amount, and then the other steel will yield, and finally the beam will attain its ultimate strength. Whether the steel will yield first or the concrete will reach its ultimate capacity depends on the design. If it is an under reinforced section properly designed, then the steel will yield before the concrete crushes. For a prestressed concrete beam, the cracking is at a higher load, and then the steel will yield to reach the ultimate strength. The effect of prestressing force is explained for a beam under pure torsion with a concentric prestressing force PE. What we are observing for this section is this beam is subjected to a pure torsion due to the torque T, and it is also subjected to a concentric prestressing force, and this concentric force will have compression, uniform compression throughout the section, and that will lead to an increase in the cracking load. For a point at mid depth of the longer side, which is denoted as element 1, there is normal stress due to the prestressing force, which will be denoted as FPE. Thus, the difference between the previous case of pure torsion and pure torsion along with prestressing force is that The element at the mid depth of the long side has not only has the pure shear due to the torsion, but it also has the axial compression due to the prestressing force. This will change the inclination of the principal stresses. Here the inclination of the principal tensile stress sigma 1 is larger than 45 degree, and the principal compressive stress, the inclination is lower than 45 degree. Since the crack is perpendicular to sigma 1 and it is parallel to sigma 2, the inclination of the cracks will be lower than 45 degree. The inclination depends on the amount of prestressing force. If we draw the Mohr circle for that element, we find that the vertical face will be denoted by a point whose coordinates are minus FPE, which is the normal stress, and tau, which is the shear stress. The horizontal surface will be denoted only by this point on the vertical axis, which is only the shear stress, and the principal stress magnitudes are now different. Sigma 1 is much lower than sigma 2, and this is the benefit of prestressing, that the principal tensile stress is reduced for a certain torque. Hence, once the cracking torque is higher as compared to a reinforced concrete beam, how much will be the cracking load depends on the amount of the prestressing force, and the inclination of the cracks also will be less than 45 degree, as we have seen for beams under flexure and shear. The formation of cracks is as follows, that with the increase in the torque, we will observe cracks in the beam which are inclined at an angle less than 45 degrees to the axis of the member. The crack width will be smaller, and the expansion of the beam that occurs for a reinforced concrete beam will not be observed here much. It of course depends on the amount of the prestressing force, and the behavior of the beam will be better in presence of the prestressing force. If we compare the formation of cracks for a reinforced concrete section and a prestressed concrete section, we shall observe that for a reinforced concrete section, the cracks first form at the mid depth of the long side, then we observe cracks at the mid depth of the shorter side. As the torque is increased, the cracks get connected and they form spiral cracks circulating the periphery of the beam. As the torque is increased, the cracks open up, the steel bars take stress, and after the yielding of the steel bars, the cracks are further increased and the length of the beam gets increased. Whereas, when we apply a compressive force in the section, the cracking load is much higher, the angle of the inclination of the cracks is now smaller than 45 degrees, the cracks do not open up, and the number of cracks is also less as compared to the non-prestressed section. Thus, this figure shows the benefit of prestressing a beam which is subjected to torsion. When a beam is subjected to simultaneous flexure and torsion, the benefits of prestressing are observed. Earlier we have studied the analysis for flexure, then we studied the analysis for shear, and now we are studying the analysis for torsion. And what we observe, that when the prestressing is applied such that it is within the allowable stresses of concrete at transfer, then the behavior under service load gets better in presence of prestressing force. The cracking load is higher and under service conditions the beam may not have any cracks, and also the durability of the beam becomes better in absence of the cracks under service loads. Thus, in presence of prestressing force, the cracking is at a higher torque. After cracking, the crack width of a spiral crack is low. Thus, the aggregate interlock is larger as compared to a non-prestressed beam under the same torque. Hence, the torsional strength of concrete increases in presence of prestressing force. This is accounted for in the expression of Tc. In presence of the prestressing force, the cracking in the concrete occurs at a higher torque. That itself shows that the concrete will have a higher resistance to torsion in presence of the prestressing force. And then, even after cracking, since the prestressing force is reducing the crack width, there is better aggregate interlock at the interface of the cracks, and the resistance of the concrete is sustained, and hence the behavior is better. The twist is smaller even after the cracking of the concrete. Whereas in a reinforced concrete section, if the torque is increased, then the member tends to have more number of cracks and it has larger crack width. The aggregate interlock is lost and the capacity of concrete to resist the torsion gets limited. Thus, the benefit of prestressing is that it checks the growth of the cracks in the concrete member, and hence it increases the capacity of the concrete, which will be reflected in the expression of Tc that we shall see in our next class. The expression of Tc will involve the prestressing force that is applied in the member. Thus, in today's lecture, we first studied that what are the types of torsion that comes in a civil engineering structure. We first had two types of torsion comes in the structure. One is the equilibrium torsion and another is the compatibility torsion. In equilibrium torsion, a statically determinant member is subjected to torsion due to eccentric loading, and this member can be analyzed based on the equilibrium equations only. Since there is no scope of redistribution, these members have to be designed for torsion, and the equations that we shall be seeing later on addresses the members which are specifically designed for equilibrium torsion. The second type of torsion, the compatibility torsion, occurs in an indeterminate system like a grid beam system, where the secondary beam applies some twist in the primary beam. Now, if the primary beam cracks due to the twist, then its torsional resistance is lowered and the secondary beam is considered to be simply supported in between the primary beams. In case of a compatibility torsion, we may not design the beams for torsion if we are designing the secondary beams as simply supported beams. The code allows us to neglect the effect of torsion in case of compatibility torsion. Next, we also learned that the analysis and design for torsion is simplified in the code. It is based on equilibrium forces only, and that too it is only at the ultimate. We do not study the compatibility of strains between concrete and steel or the constitutive relationships of either of concrete or steel. We consider only the ultimate strength of each material at failure. Next, we studied the stresses in an uncracked beam. To understand the behavior of a reinforced concrete beam, first we studied the behavior of uncracked beam, which can be considered to be homogeneous. The steel can be neglected before cracking. For an uncracked beam, we found that the shear stress that is generated due to pure torsion is maximum at the mid depth of the longer side, and if we increase the load, the principal stress is maximum at the mid depth of the longer side. The principal tensile stress is inclined to the axis of the beam, and the crack that forms perpendicular to the principal tensile stress will be inclined at an angle of 45 degree to the axis of the beam. The stress conditions in an uncracked beam helps us to understand the formation of cracks of a beam under pure torsion. Next, we moved on to study the crack pattern under pure torsion. What we have observed that in a rectangular section, the cracks first occur at the mid depth of the longer side. With increasing torque, there will be cracks at mid depth of the shorter side, and with further increase in the torque, the cracks get connected and they form a circulatory pattern around the beam. The concrete forms compressive struts carrying compression, and the steel bars act as ties which hold these compression struts. The struts and ties form a space truss which resist the torsion. We have also observed that the resistance comes mostly in the peripheral region of the beam. The region which is inside can be considered to be inactive in resisting torsion. Hence, we see that in bridge decks which are subjected to substantial torsion, a box girder is adopted because a box girder is efficient in the utilization of the material in resisting the torsion. There was another concept which we had studied, which is the thin wall tube, which comes from this observation of the resistance of torsion in the peripheral region of the member. Next, we moved on to understand the components of resistance for pure torsion. The torsion is resisted both by the concrete and the steel bars. The concrete resists the torsion by compression in the struts, and the steel bars are in tension which hold this compressive struts. Thus, what we see is that after the cracking of concrete, there is a redistribution of stresses between the concrete and steel. In the concrete, since it is weak in tension, it is not able to carry the tensile stress much after cracking. It primarily carries the compressive stress, whereas the steel bars carry the tensile stress, and the concrete and steel form a space truss. The components can be identified in two groups. One is TC, which is the contribution of concrete to resist the torsion, and the other is TS, which is the contribution of steel to resist the torsion. In our design, we shall find expressions of each of these quantities at their ultimate. As I said before, that we analyze a section only for their ultimate strength, where the code gives us expressions of TC and TS for a beam at their ultimate state. Next, we went to understand the modes of failure of a beam. For a beam under pure torsion, after the formation of the struts, if the beam is under reinforced, then the steel bars will yield. It will lead to an expansion along the length of the beam, and finally the concretes will crush, and the failure surface is not perpendicular to the axis of the beam. It is a curved surface which is inclined to the axis of the beam. Now, when a beam is subjected to combined flexure and torsion, then the analysis gets even more complicated. The skew bending theory is used to analyze a beam which is subjected to combined flexure and torsion. In this theory, the plane of failure is considered to be a planar surface which is inclined to the axis of the beam. This planar surface generates due to a resultant moment which is the resultant of the flexural moment and the torsional moment. Three modes of failure are defined, which are the discrete modes from a broad spectrum. The first mode is the modified bending failure, where the beam has substantial flexural moment and small torsional moment. The concrete at the top crushes and the steel at the bottom is under tension. The effect of torsion is that the plane section does not remain plane anymore. The failure plane is inclined to the surface, but still the concrete at the top gets crushed, which is similar to a beam under flexure only. In the second mode of failure, which is the lateral bending failure, this is observed in beams with thin webs and when the torsion is substantially high. What we find is that the crushing is occurring at the side of the beam, and in the other side the steel will be under tension, and in this, since the crushing is occurring at the side, it is called as a lateral bending failure. Finally, in the third mode of failure, we observe that here the effect of flexure is very small, but the torsion is substantially high, and under torsion the crushing can occur at any side of the beam. Now, if the top steel is small, then the crushing will occur at the bottom, which is actually the opposite of flexure, and this is called a negative bending because the crushing is occurring at the bottom and the steel at the top is yielding. In our design, we shall observe that these three modes of failure has been addressed, and we want to have a capacity which will be adequate for the beam to resist the ultimate torsion. Finally, we went into understand the effect of prestressing force. What we have observed is that due to the prestressing force, the principal tensile stress gets reduced, the angle of inclination of the cracks is small than 45 degree. After cracking, first of all the cracking load is higher, and after cracking the crack width is not large, the aggregate interlock is retained. The capacity of concrete under prestressing force is larger, and this is the direct benefit of applying prestressing to a member under torsion. In our next class, we shall move on to the analysis of the members at ultimate, and we shall get familiar with the design equations. Thank you.